problem 2 from homework 22. And so we have a motor with some gears and a pulley. So we're going to just make the simple hoist. And so gear A is 3 kilograms and a radius of 50 millimeters and a radius of gyration of 50. Gear B is about 3 times the mass and three times the radius. Its radius of gyration is 125 because it probably has some maybe holes in it or something, or weight reduction, mass reduction means. So it's a little, actually its radius of gyration is actually smaller than just being a disc. And then the pulley is 1.5 kilograms, so it's not much. And its radius is 75 and its radius of gyration is 50. So there's this external torque that's being placed on it by the motor of 25 newton meters, and this cylinder has a mass of 10 kilograms and the motor has an efficiency of 85%. So we want to determine the electrical power delivered to the motor when the pulley has rotated 10 times. So really what we're asking here is for the RPM, or the angular velocity, and then with that we're going to be able to actually get the power delivered, and then we have to increase it because the electrical power it's got to be more because the motor is inefficient. So let's see, we'll start out by getting the moments of inertia, mass moments of inertia of the various parts. So I'll get IA is going to be the mass of A times Ka squared. So 3 times, and Ka is 0.05 squared. So this is going to become a small number. And I'm going to have this one solved out as an Excel thing. So I'll keep it in scientific notation, and these are kilogram meter squared. IB should be slightly more, slightly, but that radius of gyration is 125 here. So 0.125 squared times 9 is, keep it in scientific notation, E minus 1 kilogram meter squared. And then the last one is D. So we get the mass of D times KD squared. So that ought to be pretty small. Got a small mass, got a small radius of gyration, so 0.05 squared times 1.5, yeah, 3.75. Oh, it makes sense that it's 1/2 of it, duh. E minus 3 kilogram meter squared. Alright, so it's starting from rest, so its kinetic energy is going to be 0. We might want to write some relationships before we go any further between the rotation of this and the height, right? Well, first off, this is going to rotate clockwise, which makes this rotate counterclockwise, which lifts this, right? So in the beginning, it has, we'll use that as the datum, and then it's going to rise. Because we only said it was going to be 10 revolutions, right? We didn't necessarily say it was up or down, so we just determined it must be going upwards, right? And the number of revolutions of D, right? So we could say the height is going to be delta theta D times RD, right? And the number of revolutions needs to be turned into radians. So we go 10 revs and then 2 pi radians per rev to turn this into radians, and then the distance is going to be the radius of d, which is 0.075 meters. All right, so let's see. I don't know. I made this, so I'm not sure it's going to have meaningful numbers, but we'll see what happens here. Times there, but now we have to go 0.075 times it. So that means it's going to go up 4.712 meters. It's going to be the distance of cable that has wrapped up to this thing, so that's why that C is going to move that there. We call that HC. Why no? Or delta YC. I like delta YC. And I could go 1 to 2, but it's kind of obvious we only have 2 states in this one. Also, we want to get the omegas related. All right, so let's say I want everything in terms of omega A, because that's the thing I'm actually going to solve for initially, because we want to get the electrical power, but we know that power is torque times angular velocity. So let's look for the angular velocity of A. So let's see. So I'll start out by going backwards and say velocity of C is going to be the angular velocity of B times RB. I labeled this wrong over here, by the way. Would be okay. And so RB. So we can say that the angular velocity of B. No, I think I'm okay right there. I think I'm all right. Now we're also going to have a shared velocity, and sometimes I'll even draw in an arbitrary point right here. It's going to be going this way right here, right? So B rotates that way, causes a velocity here, but this rotates that way. It has they share the same velocity. So I'll write that the omega A RA is going to be equal to omega B RB. So omega B is equal to R. Let's see if I'm going to say this the right way. RA over RB times omega A. All right. So now I have omega B in terms of omega A. Now I need the same thing right here. So I'm going to stick this back into there. So, oh, that doesn't make sense. VC, okay, well, that should be RD. That's why. Okay. All right, so velocity C is omega B. This whole omega. I don't need to call omega D equals omega B, so I could just use those interchangeably. Okay, so velocity of C is going to be RA RD over RB. Velocity, nope, omega A, sorry. All right, so now I think I have it. I'm going to use work energy, and what I want to find, we'll start with KE1 plus PE1 plus work from 1 to 2. All right. Ooh. We need, yes, we need the number of rotations that of A. That's another thing I'm going to need before I go any further. I'm just doing it because I need to, I would write maybe this over to the side on another piece of paper. But I do need, because I have external work, I need to have torque times the angle that it gets turned through. So we need to relate that. So, damn. How do I want to do that? I'll say delta theta D is equal to delta theta B. All right, so we know that. And we could actually say, just from this relationship here, we could say that delta theta A times RA is equal to delta theta B times RB. Therefore, delta theta, write it down here, delta theta A is equal to RB over RA times delta theta D, which we're going to write down. This is B is, it's a ratio, so I don't really care about the ratio there. I don't need, I could just keep that as millimeters, and here is 50. So it's going to be 3 times the number of rotations of A as the number of rotations of D, and we never did find that out. So, and we'd like to do this in radians, so it's going to be 10 this revs times 2 pi, right? 2 pi radians per rev. So 150 divided by 3, times 10 times 2, and then times pi. So we get 188.5 radians. Okay, now I'm ready for my big picture here. KE1 plus PE1 plus work done between states 1 and 2 is going to be equal to KE2 plus PE2. That should be right. All right, so KE1 starts from rest. PE2, we're going to start at the datum, right? So we're just going to increase the potential energy, so we're starting with a 0 potential energy. The work between 1 and 2 is going to be the torque of A times delta theta A, right? So it's going to be this torque times the angular displacement, or 25 times 188.5, and so 188.5 times, this is a lot, 4,713 Newton meters. KE2, I didn't leave myself a lot of room here. I'm going to go to another page here in a second, but still kind of cramming it all in. We're going to have 1/2 AIA omega A2 squared plus 1/2. Now we have to go, we have to turn, now both B and D are rotating at the same speed, so I'm just going to combine them. And we can do that because they're about the same axis anyway. It's omega B2 squared. And then plus the translational kinetic energy of mass C. So it's C2 squared. And now we need to replace omega B with this, and VC with that. And I feel like I'm going to cram that into the next page, so cram that down below somewhere to the next page. But don't worry, we're almost done. This is 2 continued. And so KE2, we we get 1/2, let's put all this in here, 7.5 E minus 3 times, and we want omega A squared. Got that. 1/2, and we had to add these two together, which could have done before. It's supposed to be minus E minus 1 plus 3.75 E minus 3. And then omega B squared. Omega B is RA over RB times omega. So that's RA over RB. RA is, and this is a ratio, so we can use millimeters, over B, 150. Yes, okay, that makes sense. That's going to be omega A 2 squared plus 1/2 mass of C, 10 kilograms. And the velocity of C, though, is going to be this right here. Now, we have to be careful. This does need to be in millimeters right here, this RD, right? Because these might cancel out, but that one doesn't. That would have been a slippery slope, I'll tell you what. So I guess it'd be confusing, but I guess I'll leave it there. 50 divided by 150, but now I got to get the RD. Definitely needs to be in 0.075, and then omega A2 squared. Okay. I think I got all that right. So what I really want to get is something to multiplier in front of this. So 7.5 E minus 3, 2 divided. All right, now here's the one we got to go. That's going to be 1/3 squared. Divided by 2 there. And then those two, 4, whoops, I could just plug that in as 1406, and then 3.75 E to the 3 minus atom, whoops, okay, I see what I did. I did something wrong. Atom, multiply them, and then atom, yeah. And then this last one is, let's see, 0.075 divided by 3, really, and then squared times 5. And that doesn't affect it much. So we're going to get 1.489 E minus 2 omega A2 squared. And then lastly, PE2 is going to be mCg times delta YC 1 to 2, or 10 times 9.81. And we already found what that was going to be, didn't we? We said after 10 revolutions, yeah, 4.712 meters. So 4.712, 9.81 times 10 times. So 462.2 Newton meters. So that doesn't really do as much as this input here. So the input's going to connect for the kinetic energy. So we put these in for what we know for inside here. And 4713 seems like a lot. Maybe I should have made the torque less. Whatever. And then go 1.489 E minus 2 omega A2 squared plus 462.2. I'm going to get omega A2 4713 minus, put it up big there so it didn't change it much, and then divide it, and then square root it. Jeez, that's a lot. 534.2 radians per second. And just out of curiosity, let's see what that is in terms of revolutions per minute. So that's per second. So per minute, we can multiply it by 60, but then you divide 2 pi that's still a lot, right? That's 5,101 revolutions per minute. That's like huge. That's crazy. That's fast. That didn't make a lot of sense. I should have messed around with the numbers. But anyway, so like the power, like the delivered power, is torque right here. So put it in units here, 25 Newton meters times 534.2 radians per second. It's going to be a lot. That's 13,300 and did I do that right? Yes, I did. And 56 Newton meters per second, which is the definition of a watt. Therefore, just say I just say del for my delivered here, and instead of writing up here, is going to be 13.36 kilowatts. Didn't make that W very good. But the electrical power is going to be the delivered divided by the efficiency of the motor. So 13.36 divided by 0.85. And we end up with 15.71 kilowatts. So the answer is electrical power is 15.71 kW. Can't make my W's. So there you go. And let's box it in.